Hi, my name is Vincent. I tested the effect of crab bridges lengths on their bending and braking behavior. So for this project, I built 5 different lengths of truss bridges, and each section of the truss bridge is modular, which means that it can be expanded to a longer length. So a truss bridge is a bridge that really focuses on distributing the weight that's applied to it. As you can see by this, if a weight is put on the middle, then it's distributed throughout the beams in 3 forms of stress. One of them is compression, which means if you squish something together, the molecules are going to get closer together. That's one of the forces acting on a truss bridge, mostly on the bottom beam if there's a force applied to the top. Another one is tension, which means it's being pulled apart. This happens on the top beam of the bridge when it experiences a downward force. Shear stress also results when something is put on the top of the bridge, because the supports are pushing up on the bridge and the middle of the bridge is being pushed down. And shear stress gets its name from scissors, or shears, as they push in opposite directions and put that type of force on an object, and this happens in the truss bridge. So to test the bending lengths for truss bridges, first I had to assemble 5 truss bridges, which were made out of plastic building parts, and then I made an apparatus of a bucket filled with weights attached to a string on the 2 joints, as you can see here. So once that was done, the 2 tables were rolled into each other and the bridge was put on top of them, clamped securely onto each side of the table, and the bucket was draped from the middle. And then consistently weights were added to the bucket, and using a ruler that was attached to the back, I was able to measure precisely the amount of bending that was for each amount of weight that I put on it. And so as you can see, the results were fairly linear, with a little bit of a y-intercept, which might have been attributed to the bucket at the beginning. The linear results allow us to infer that that as the weight was put on, the bridge bent at an increased rate, which really emphasizes the fact that the truss bridge redistributes its weight and it doesn't have actually performative bending. And then each of the slopes of the 5 bridges were graphed against the length of the bridge. And this led to an interesting conclusion, because it was in the form of a polynomial function. So obviously as the length increases, it gets even more weak than the previous bridge, not at a linear rate, but at a polynomial rate. Then, contradictory to the hypothesis, it was found that the braking length, the length at which the bridge broke, increased as a function of when the weight was put on it. And this was fairly linear, although the fit's not that great. Another important thing to keep in mind about this project was the way that the bucket was attached to the bridge, which was in the 2 joints on either side. As weight was, and as it actually broke, they broke in some interesting methods, especially that they didn't break in the actual joints normally that the weight was applied, which sort of shows that the truss bridge really focuses on redistributing the weight throughout the beams. For example, the two joints that were subject to downward force were these 2, but it actually broke here. And yeah, these results about the redistribution were not fully tested in this experiment and merit further investigation.